All right, so a brief review for finding the rates of change and limit values. So over the past few days, we have been talking about how to find a limit. And there are a couple techniques that you can use to find a limit. The first of those techniques is to simply substitute. So the very first thing you want to do when you are trying to find a limit is to substitute. If you substitute and you get a numerical answer, then you're done. It means that the function is continuous as x equals a, and your limit is the same as your function value. If you substitute and you get 0 over 0, that is called the indeterminate form, and that means that you need to simplify through factoring. So if after you substitute you get 0 over 0, you need to try to factor. If you substitute and you get a number in the numerator and a 0 in the denominator, then there is no limit, and that's a DNE. If you get 0 in the numerator and the denominator, again, you have to keep working. So the limit as x approaches 5, 2x squared minus 3x plus 4 is a polynomial function. Polynomial functions are continuous always. So since the polynomial is continuous, then we know that this is continuous, and therefore I should get a nice number. So when you take the limit, you write down the limit until you plug the limit in. So if my next move is to plug in 5, I do not need to write the limit anymore. So I get 2 times 25 minus 15 plus 4. So you get 50 minus 15 plus 4. So we get 54 minus 15, which is 39. So again, when we're working on these types of problems, you really shouldn't need a calculator unless they ask you to find something on a calculator. Okay, the limit as x approaches -2. So sometimes our gut sees this and they say, I should try to factor and simplify, but there is nothing in this problem to really allow you to factor and simplify. There's no factors of -1 that sum to 2, and the denominator can't be simplified. In this case, if you plug in -2, we get -8 plus 8 minus 1 over 5 plus 6. So we get -1 over 11. We get lucky, and then when we substitute it into this crazy messy function, it's a nice pretty number. So the first two examples, pretty easy. Simple substitute in, get a number out. So that is always our first thought. Substitute in to get a number. Now, in example 3, if the first thing you do is substitute, you get 1 squared minus 1 over 1 minus 1, which gives you 0 over 0. Again, this is called the indeterminate form. The indeterminate form tells me that I can simplify further. So I'm going to rewrite the limit as x approaches 1. And again, now since I'm going back to the original limit, I need to write the limit. And I'm going to take the numerator and rewrite it in factored form. So the numerator is a difference of squares. We can rewrite that as x minus 1, x plus 1. Upon doing so, we're able to cancel the x minus 1 from the numerator and the denominator, which means this limit or problem behaves exactly like x plus 1. It just means that my domain does not include 1. So the domain is all reals for this problem except x equals 1, which means that f of 1 does not equal the limit, but that the limit is approaching it from both sides. So the limit as x approaches 1 of x plus 1 gives 1 plus 1, or 2. Example 4. This is actually a preview of what we're going to look at in the next unit in chapter 2. This is called the difference quotient. The limit as h approaches 0 of a function minus another function all over h. This is a way of finding that instantaneous velocity. So again, this is called the difference quotient. It's a way of finding instantaneous velocity. If you plug in 0 to start, we get the indeterminate form, or 0 over 0. So we know, okay, I got to do some algebra. For this problem, algebraically, the only thing I can do is what? Algebraically, to try to simplify this, what's the only thing I really can do? Even before I do that, what can you do? Yeah, I can FOIL, right? So there's an h down in the bottom. Multiplying by h over h, we're going to see why that would help, but wouldn't help a lot, because if you get h squared, you're still going to get 0. If I FOIL, though, I get the limit as h approaches 0 of 9 plus 3h plus 3h plus h squared minus 9. Well, I get positive 9 and negative 9. So they cancel. Three h plus 3h is 6h plus h squared all over h. So now that my 9's cancel, I have 6h plus h squared. So in my numerator, I can factor out an h. And boom, there's kind of that h over h you were looking for, Bethany, but it happens naturally. So this simplifies to the limit as h approaches 0 of 6 plus h. We plug in 0 for h, and we get 6. So, don't think you care a lot. If this problem had asked you to find the instantaneous velocity, you just found the instantaneous velocity at 3 to be 6. And this is on an x squared function. You'll see all of that soon. Okay? So even without plugging this in, I see t squared in my denominator. I know the denominator is going to be 0. I know it. So you get the square root of 0 squared plus 16 minus 4 over 0. Square root of 16 minus 4. And I get 0 over 0 or indeterminate. Again, the minute you get 0 over 0, you know you can simplify. It means algebraically a limit exists. I just need to go about finding it. To get rid of a square root in a limit problem, we multiply by the complex conjugate. The complex conjugate is a really fancy way of saying the missing piece on a difference of squares. If you look at this right now, and I put parentheses around this, does that not look like a variation of a minus b, a plus b? Which was just going to become a squared minus b squared. So the complex conjugate will never have the middle terms of FOIL because they're naturally set up to cancel each other. So you're really doing first minus last. So square root times a square root go away. So you get t squared plus 16. Outer inner terms are canceling because they are identical to each other. Minus 4 square roots of t squared plus 16 plus 4 square roots of t squared plus 16 cancel. Negative 4 times 4 is negative 16. Do not FOIL, distribute, multiply anything with your denominator. Just gotta carry it along. Because naturally, plus 16 minus 16 cancel. So it leaves you with t squared over all of that. But technically, there's kind of like a factored out t squared. So t squared over t squared becomes 1. So this becomes the limit as t approaches 0 of 1 over square root t squared plus 16 plus 4. Let's try plugging in 0 again. Once I plug in my number, I no longer write the limit, but you'll notice that I wrote that limit every single time I wrote an equal sign. So limit equals, limit equals, limit equals. You have to be consistent. Not writing the limit before you plug the limit in is not the same. So we get 1/8. Okay. The limit as x approaches 4. So again, first thing you have to do is technically plug in your 0 and show, or plug in 4 to show it's 0. Oh man. Now we're going to look to clean this up algebraically. In the numerator, I can see x squared and x, so I'm going to factor out an x. And then in the denominator, that looks like a factorable quadratic. So factors of 4 that sum to 3 are 4 and 1. Since it's negative, you get negative 4, positive 1. I notice that I have x minus 4 on top and bottom, so they cancel. So this simplifies to x over x plus 1. Plug in my 4, and I get 4/5. So we know again that x does not equal 4. It's not in my domain, but that the limit as x gets close to 4 is 4/5. So on the graph, there is probably a hole at 4/5. Okay? And then the last type of algebraic example would be something like the limit as t approaches 0 of a fraction minus a fraction. So if you look at the denominators of the fraction, are they the same? No. So once we plug in our 0, we see that we get 1 minus 1 on top, 0 over 0 on bottom. You still get that 0 over 0. So we know if we want to add, subtract fractions together, they have to have a like denominator. So that first part of the fraction can't really be changed much. But the second part, I could factor out a t, and I see that it becomes the quantity of t times t plus 1. Well, now that means the least common multiple is t times t plus 1. It means I need both fractions to look like that. So what we're going to do is multiply the first part by t plus 1 over t plus 1. So it's like multiplying by 1, but it gets me my common denominator. Once I have a common denominator, then I know that I can subtract my numerators. So plus 1 minus 1 cancels. I have t over t again, so that cancels. So the limit as t approaches 0 becomes equal to 1 over t plus 1, which means that when I plug in 1, the limit as t approaches 0 of this function is 1.